It's my pleasure and honor this morning to introduce to you one of our, Nobel laureates, Professor Dan Shechtman. Dan was born in Israel in 1941 in Tel Aviv, obtained his BSc degree in mechanical engineering in 1966 from the Technion, also his master's degree in material engineering from the same institution, 1968. And his PhD was obtained in 1972, also from the Technion in material engineering. In 1975, he joined the Department of Material Engineering at the Technion, where he conducted his research in the Louis Edelstein Center and in Wolfensohn Center, which was headed by him. He served on several Technion Senate committees and headed one of them. He has got an extensive academic work outside of Israel. I'll mention those things. Professor Shechtman was a fellow at the Aerospace Research Laboratories at Wright-Patterson Air Force Base at Ohio, where he studied for 3 years the microstructure and physical metallurgy of titanium aluminides. In 1981 till the 1983, he spent another sabbatical leave at Johns Hopkins University in the USA, where he studied rapidly solidified aluminum transition metal alloys, where he discovered then the icosahedral phase, which opened a new field of quasi-periodic crystals. In 1992-94, he spent a sabbatical also at the National Institute of Standards and Technology, NIST, where he studied the effect of defect structure of diamond on its growth and properties. Professor Shechtman joined the Iowa State faculty in 2004 and spends almost 5 months a year at Ames, I think until now. Yes. Professor Shechtman obtained his Nobel Prize in Chemistry in 2011 on quasi-crystals. He experienced hostility from the 2-time Nobel laureate Linus Pauling, who fought against quasi-periodicity in crystals, and he appeared to be wrong at the end. Through Shechtman's discovery, several other groups were able to form similar quasi-crystals materials. And today we'll know better about the quasi-crystals. Similar quasi-crystals materials that could be used in large number of applications. Now, also Professor Shechtman was a recipient of many Israeli and international prizes, of which I'll mention only few. He obtained the European Material Research Society Award in the 2008. He also obtained the Emmet Prize in Chemistry in the 2002, which is a prize coordinated by the Prime Minister's Office. Also, he obtained the Muriel and David Jacquenot Technion, it's a Technion Award for excellence in teaching in the year 2000. Also, he obtained the Grigory Aminov Prize of the Royal Swedish Academy of Sciences in the year 2000. And the Wolf Prize in Physics in 1999, and as I said, many other prizes that there's no time to mention them all. Of course, he's got nothing to mention about his international articles, which are huge. This morning, Professor Shechtman's lecture will be entitled Quasi-Periodic Materials, a Paradigm Shift in Crystallography. Professor Shechtman, the floor is yours, and thank you very much.
Thank you, Hassan, for your introduction. Everything is true, but this is not the most important thing to know about me. What is important to know is that I have 10 grandchildren and 4 children and 1 wife. Now you know me. Okay. So the talk, as Hassan said, quasi-periodic material, the paradigm shift in crystallography. I will explain it in such a way that even the lawyers amongst you will understand me. And that's an achievement, because this is a complex issue. Okay. In order to understand what happened with the discovery, let me take you back to the mid-80s, the mid-1980s. In the mid-1980s, there were 3 surprising discoveries on the structure of matter and its properties. And they came year after year, 1984, 85, 86, and all these 3 discoveries received the Nobel Prize, which is quite an amazing fact. Chronologically, in this order, 1984, quasi-periodic crystals were discovered, and the names on the first publication is my name, Ilan Blech, Denis Gratias, and John Kahn. I will tell you about these people. Next came fullerenes, 1985. Harry Kroto and his colleagues made their discovery, and a year later, high-temperature superconductivity was discovered by George Bednorz and Alex Muller. And this is a set of very interesting discoveries. Now, when high-temperature superconductivity was announced, everybody was happy. Of course, superconductivity was discovered in the beginning of the 20th century, 1909. But everybody thought that superconductivity will be up to about 30 degrees Kelvin, and there were theories to explain it. And here we are with high-temperature superconductivity. High temperature meaning liquid nitrogen temperatures. It's not very high, but it is becoming more useful. And everybody was happy. There was no objection to the discovery. When fullerenes were discovered, there was some objection, so tells me Harry Kroto. A few papers were against the model, C60 of atoms, but it died very soon, and everybody was happy. Here is another way in which carbon atoms can order. So we have diamond, we have graphite, and we have fullerenes. And this was the beginning of a large field of nanomaterials that everybody is working on today. But when quasi-periodic crystals were announced in 1984, they met a lot of resistance. The international community said, no way, these materials cannot exist. And the objection lasted for 10 years. And I will tell you about it. I'll tell you why it was like that. But on the other hand, there was a growing community of young, eminent, avant-garde scientists who took my discovery and made it into a science. So this is the background. But in order to understand my talk, we have to understand a few basics in crystallography. Everybody will become an expert in crystallography in 5 minutes. And we will learn something about order, about periodicity, and about rotational symmetry. First, let's say something about order. Here is a drawing on a plane, 2-dimensional drawing, of atoms. And they are clearly ordered. There is order here. That means the following, that if I ask you to continue this in this direction, or that direction, or any other direction, you will know exactly how to do it. You can measure the distances, and you can continue and make this grid larger. This is the order. This is all you have to understand about order. This structure is not only ordered, it is also periodic. What does it mean? It means that if you look at this direction, you see that there is periodicity here. The distance from here to here equals the distance from here to here, and so all the distances are equal. You take this distance, you multiply it by any integer. By 2, you get here. By 3, you get here. By 4, you get here, and so on. This is periodicity. It's a periodic structure. And because this lattice is periodic, there is periodicity in every direction that you choose. For instance, in this direction, there is periodicity. You see? The equal distances. And in this direction, there is periodicity. Equal distance. Any direction that you choose, there is periodicity, because this is a periodic lattice. Okay. Now, here is an example of periodicity. You see, let's go back here. Here, the motif is one atom, one atom, one atom, one atom, one atom. But this motif can be very large. Ada Yonat, who gave a lecture yesterday, showed you that he took the ribosome, which is a huge molecule, and made the ribosome stand like soldiers, 1, 2, 3. She made a crystal from ribosome. So in this crystal, the motif is one atom, but this motif can be very large. Okay. Now, let's see that there is a larger type of periodicity. This is a fence of my hotel in Easter Island. And Claude Tanucci can recognize this fence. We were there together. And if you look at the fence, you see that there is periodicity here. But the periodicity is not just one bar. It's something like this. Look here. This is the period. Okay? This is the motif. And here's another one, another one, another one, another one. So the motif is larger than one atom or one bar. Larger motifs. And the motifs can be very, very large. That's all about periodicity. Now, what about rotational symmetry? Here I have the same lattice as before, but I added a little handle here so that you see what happens when I rotate it. And I can rotate it 90 degrees, and it looks the same, except for the handle. It looks the same. Oh, my Skype is on. I hope they don't want to talk to me. Okay. I had a few embarrassing moments with this Skype thing. 180 degrees, 270 degrees. Every time it looks the same. And 360 degrees, it looks the same. You can turn it 4 times, and each time it looks the same. This is why this lattice has a 4-fold rotational symmetry. 4-fold rotational symmetry means you can turn it 1/4, it looks the same, half, 3/4, and it looks the same every time. This is about rotational symmetry. Let me show you a few examples from our own life. A card. This card has a 2-fold rotational symmetry. You can turn it 180 degrees, another one, and it looks the same. This set of triangles has a 3-fold rotational symmetry. This flower, 5-fold. This pizza, 6-fold. And you can have, this is a motif. A motif can have any rotational symmetry that you want. Not so is the lattice. And let's talk about it a little bit later. Now, let's say a few words about crystallography, because my discovery made a paradigm shift in the science of crystallography. I don't want you to read it. Let me just talk. Crystallography is an ancient science. People in the Greek time and before looked at crystals that they have found in nature or that they made in their kitchen, and they saw that they have facets, nice facets. And they measured the angles between the facets, and they deduced that if they, for example, let's say if the crystal looks cubic, like a cube, then probably there are atoms inside, little particles that are arranged in a cubic way. And they went beyond that, and they developed the field of crystallography, or so-called crystallography. But they did not have the tool to measure anything, and they did not have the tool to prove that what they are saying is correct. In 1912, however, this is 101 years ago, a German scientist named von Laue performed a wonderful experiment. He performed the first X-ray diffraction from a crystal. And he proved in one experiment 2 very important facts. Number 1, that X-rays have a wavy nature, like light. X-ray is a short wavelength light, if you want. And he showed also the crystals are indeed ordered as people thought before. This was the proof. And immediately, a science was created, and the science was named crystallography. And that science is and was ruled by a committee or a union that is called the International Union of Crystallography. Now, you have to understand, the International Union of Crystalography is a body of hardcore mathematical crystallographers. These are no-nonsense people. Everything must be proven from the very basics, mathematical crystallographers. And the tool of choice was X-ray diffraction. And the science was named X-ray crystallography. If you came with another way of proving things, like electron diffraction or neutron diffraction, no. You bring us X-ray diffraction, then we can talk. And this body is harder than a Latin synod. I mean, these are very strict people. Why is it important? You will see later. So this is the science of crystallography. We don't need to read this. Now, von Laue, who studied his crystal, which was ordered, and therefore crystal, found also that his crystal, I think it was zinc selenide, the first one, it was also periodic. It was ordered and periodic. And now you know what order is and what periodicity is. In hundreds of thousands of crystals that have been studied by tens of thousands of eminent crystallographers around the world, for 70 years, all these crystals were ordered and periodic. And there was no exception. Order was synonym to periodicity by experiments. There was no theory behind it. Order can be other things, but people said, yes, it can be other things, but crystals are always ordered and periodic. And so a definition came up from these hundreds of thousands of organizations. And a crystal, this is from the book X-ray Diffraction by Quality. A crystal may be defined as a solid composed of atoms arranged in a pattern periodic in 3 dimensions. A crystal is ordered and periodic. Very simple. Another definition, this is a book by Bart and Masalsky. Different words, exactly the same meaning. Atoms in a crystal are arranged in a pattern that repeats itself. Repeats itself means periodic. In 3 dimensions throughout the interior of the crystal. These were the definition of the crystal. Now you have to understand that the definition of the crystal is the foundation on which the whole science lies. What is a crystal? What do you study? We study crystal. What is a crystal? This is a crystal. Okay? Ordered and periodic. And it was, the science of crystallography was very peaceful, and the science of crystallography was a mature science. And a mature science means it's a science that you don't expect any discoveries to shake the foundation of the science. Yes, you could define new crystals, no problem. But all these crystals belong to families, and the families were known, and there was a drawer for each type of crystal. And if you find a new one, let's say a crystal with a structure DO19, wonderful, here is the drawer for DO19, welcome new crystal, put it in, and the science was peaceful. No shocks were expected in this science. Now, crystallography in 1982 can be, this is the book that I studied from Charles Kittel, Introduction to Solid State Physics. I know you cannot read what's marked in green here, so I enlarged it for you, and now you can. And he says the following. We can make a crystal for molecules which individually have a 5-fold rotation axis. But we should not expect the lattice to have a 5-fold rotation axis. A molecule can have any rotation axis that you want, but the lattice cannot have 5-fold rotation axis. Why so? Let me show you why it is. Let me take you back to the days in which I did my master's degree at the Technion. This is the late 60s, and I took a class in crystallography. And one of the questions in the final exams was, prove that 5-fold rotational symmetry cannot exist in crystals. And I proved it. I passed the exams, and this is why I'm here now. So here is the proof. Why 5-fold rotational symmetry cannot exist in crystals, in periodic crystals. In periodic crystals. This is true till today. So in order to prove it, you take 2 atoms, P and Q, 2 atoms in a lattice, and make them so that the distance between them R is the minimum distance. These are the closest atoms that you can find in that lattice. And if 5-fold rotational symmetry is allowed, then we should be able to rotate Q around P 5 times and P around Q 5 times. And let's see what happens. So here's Q, 2, 3, 4, and 5. And we should have a Q prime atom here. P, 2, 3, 4, and 5. And we should have a P prime atom here. But clearly the distance Q prime, P prime is shorter than the distance PQ. And that cannot be because we chose the 2 closest atoms. I passed that exam. OK, so this is why. Now let me show you a few examples. Diamond, as you know, is not forever, by the way. It's a metastable phase, but it is ordered and periodic. And here are, this is a picture I took many years ago of carbon atoms in diamond. This is electron microscopy. And you see here that there is order. Clearly there is order. And there is periodicity. So there is periodicity in this direction, periodicity in this direction, in this direction. In fact, any direction that you choose, you'll find periodicity because it is a periodic lattice. And the order of carbon atoms in diamond is periodic. The allowed rotation symmetries are 1, 2, 3, 4, and 6. 5-fold rotation symmetry, as well as any other symmetry beyond 6, is forbidden in periodic structures. This was the knowledge, and everybody was happy. Now, let me take you to the space which is called reciprocal space. Now we have to start thinking a little bit, just a little bit. This is the space in which the diffraction pattern exists. Remember, von Laue did X-ray diffraction pattern. I work on an electron microscope. I do electron diffraction pattern. And here is an example of an electron diffraction pattern. What you do in an electron microscopy is a big machine, and it has many, many analytical capabilities. And the capabilities are improved and developed in a very fast rate. So is the price of the microscope. So if you want to buy a modern, good microscope, you can start talking about $10 million a piece for starters. Okay, that's what's going on. But it's a very, very powerful machine. This is the diffraction pattern. What you do in the electron microscope is you take a specimen of any material that can resist vacuum, and you shine an electron beam onto it, like this laser beam. You shine an electron beam. Because it is thin, part of the beam will go directly down through and will mark a point on a phosphorus screen. Phosphorus screen is like your television screen or your telephone screen. It will mark a point in the center, and this is the point in the center. All the other points are diffracted beams. These are beams that diffract. They are scattered elastically to the size, and they are scattered by the planes, the atomic planes in that crystal that you study. So this diffraction pattern tells us a lot about the order and the structure of the material. As you can see here, by the way, this diffraction pattern exists in a mathematical space that we have developed, and it is called the reciprocal space. The real space is the space where the atoms are, where we live in the real space. Well, most of us live in the real space. And the diffraction pattern exists in a reciprocal space. It's just a mathematical space which helps us understand what we see in the diffraction pattern. Okay, and you see here, because this was taken from a periodic lattice, this diffraction pattern, there is also periodicity here. Periodicity in this direction, in this direction, in this direction. Any direction you choose, periodicity. That means the following. If you take the distance from here to here, multiply it by 2, you get here. Multiply by 3, you are here. By 4, you are here. Same here. Take this distance, multiply by 2, you get here. By 3, you get here. This is the periodicity. And periodicity that exists in the crystal in the real space also exists in the diffraction pattern in the reciprocal space. Life was simple. And then something shocking happened. In 1992, the International Union of Crystallography, that is the hard body of mathematical crystallographers, no-nonsense crystallographers, issued a new definition of a crystal. This is now a definition of a crystal. And unlike the previous definition, that was very simple. The previous said a crystal is a material in which the atoms are ordered and periodic. Simple. This is a poem. What? The International Union of Crystallography writes poems? What happened? These are hardcore mathematical crystallographers? We will read this slowly, and you see that they composed a poem. It doesn't say, this is the definition of a crystal. It doesn't say a crystal is. No. Soft. By crystal we mean any solid having an essentially discrete diffraction diagram. Very soft. And by aperiodic crystal we mean any crystal in which three-dimensional lattice periodicity can be considered to be absent. Is it a poem or what? So what happened? What happened? That the definition of a crystal had to be changed, and now it is different. This change was a paradigm shift in crystallography, and my talk is about what happened that brought this change about. 1982 was the 70th birth of crystallography. Remember 1912 on Laue, 1982, the discovery of quasi-periodic crystals, 70 years. And this was the year that quasi-periodic materials were discovered. Now, to take you to my laboratory, at the minute of discovery, I will show you my logbook from that day. And when I talk to young scientists, I tell them lesson number 1 is you make an experiment, write down what you did in a logbook. Because today you remember, next week you don't remember what you did. Write it down in a logbook. And here is an example. I must admit that the handwriting is kind of sloppy, partly because my handwriting is sloppy, but partly because this is written in the dark of the electron microscope room, and it was also written only for me. But just happened that many people see this now. Anyway, it contains a lot of information. The date is April 8, 1982. I was working on aluminum 25 weight % manganese, and this number is the plate number on the microscope. It's the film, the picture number on the microscope. Picture number 1720, I had many before and many after. SAD is a diffraction pattern, selected area diffraction pattern. And so that morning, I'm working with these materials, SAD, and then I take a picture with magnification 28,000 times, K is 1,000, 28,000 times. And I continue, and then picture number 1724, 36,000 times magnification. I look at this picture and I said, what's going on here? I will show you the picture, and I will show what is special about that picture. And then I said, okay, now I must take a diffraction pattern. I take a diffraction pattern, and I write down, I counted, and said 10-fold with 3 question marks. And then I performed a series of experiments to tell me what I found, and I will tell you about this experiment, even though I will not show them to you, because for sake of time. Okay, so this was the discovery. In the morning of April 8, 1982, beautiful day outside, and I'm in the dark of the electron microscope. The first view of the icosahedral phase. By the way, I would like to talk to the people in charge of the screening. I need 2 AAA batteries if you have, because I'm going to lose the power on this laser thing. Okay, 2 AAA batteries, maybe you can get me? Okay, this is the first view of the icosahedral phase. This is how it looked like. So what do we see here? You remember in the electron microscope, everything is transparent. So it's like a transparency. You see through the crystal, right? Because the crystals are very thin. This is the crystal right here. Here's another one. Here's another one. This material is polycrystalline material. There are many crystals in it. And some of these crystals, and this is what drew my attention, were pitch black. This is black, 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 black. This is what is called bright field image. And in the bright field image, if the crystal is black, it means that the transmitted beam has no intensity, and all the power, all the energy goes to the diffracted beams. And I have never before seen in my life such a crystal that diffracts so heavily. And I said, wow, that's strange. Now, in the Greek times, when somebody made a discovery, he would jump out of the bathtub and cry, Eureka, right? And run in the street half naked. Today, scientists don't usually do that. But instead, when a scientist discovers something different, he would say, that's interesting. Or, what's going on here? Or, that's odd. These words may mean discovery. I took a diffraction pattern. And this is the diffraction pattern I saw. This is the original one. This is it. This is the first diffraction pattern. And I look at the diffraction pattern, and it looks very, very odd to me. She said, well, what's going on? What is the rotational symmetry? And I start to count around the center. Okay, what is the rotational symmetry? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, no. Cannot be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and I write tenfold. It turns out later on that it was fivefold, but I couldn't tell by looking at this. I had to do another experiment called Kikuchi pattern. It's besides the point. But that's not all. You see, periodicity is gone. There is no periodicity in this lattice. You take the distance from the center to this spot, and you multiply it by 2. From here to here, multiply by 2, you get here. But there is nothing there. You multiply by 3, you get here. There is nothing there. What's going on? 5-fold rotation symmetry, no periodicity. Something is very, very interesting or strange here. Okay, so this is the discovery. Turns out that if you take this, I'm going to say a sentence which is wrong. You tell me why it is wrong. If you take this distance from here to here and divide by distances from here to here, you get the irrational number tau, which is the Fibonacci number 1 plus root 5 divided by 2, 1.618. Of course, you cannot get an irrational number by taking A divided by B. But this is approximately. So this came from theory later on. No periodicity, 5-fold rotation symmetry, and then I started to do a set of diffraction patterns to see all the diffraction patterns from this. I have to explain. You can take your crystal in the electron microscope, you can tilt it to any desired position, and you can rotate it. It's a goniometer. We call it a goniometer that can tilt and rotate. So you can achieve any direction that you want. And I took diffraction patterns from some of these directions. This is the 5-fold, 2-fold, and 5-fold again. And this is 5, 3, 2, 3. This is a set of diffraction patterns that describe icosahedral symmetry. I will tell you what an icosahedral symmetry is. You will be expert in quasi-periodic material, more so than in periodic material, most of you. This is what I thought I have. This is a different picture. This is a picture of diamond crystals. And diamond is periodic, as you remember. And this is a single crystal. This is a single crystal. Another one, another one. I have 5 crystals here. Forget the sigma notations. They are not important now. But what is important is that they have borders, boundaries between the crystal. This is called crystal boundary. Here's another one. So between the 5 crystals, we have 5 boundaries. And these are special boundaries. What's special about them? They are mirror boundaries. Look here. You take this line of atoms or plane of atoms, and it is reflected here, like in a mirror. Okay? This is reflected here, like in a mirror. This is reflected here, this reflected here, and so on. These are called twin boundaries, because these crystals look like twins, like matching twins. These are called twins. And I saw that I have twins in my crystal. Why did I think that? Because if you take a diffraction pattern from one of them, which is periodic, you'll get a periodic diffraction pattern. No problem. But if you take a diffraction pattern, perfect. Thank you so much. If you take a diffraction pattern from all of them together, then you get 5 superimposed diffraction patterns from the first one, from the second one, from the third one, and there are 72 degrees from each other because 360 degrees divided by 5. And this is superposition of 5 diffraction patterns with 5-fold rotation symmetry, but it's not from a single crystal. This is what I thought. And I said to myself, find the twins, record it, and forget it. I spent the whole day and days later to look for the twins in a series of very, very precision experiment. No twins. I knew from day one that there were no twins there. Why so? Because my opponent says 10 years later and 12 years later that these materials are twinned periodic crystals. Enough of that. This is just a nice picture of you can take today on an electron microscope. Look at this 10-fold pattern. These are atoms in quasi-periodic materials. The finding was done, as you saw, in 1982. My first paper was sent for publication in 1984, and I did it jointly with Ilan Blech, who was the first person to join forces with me? And Ilan Blech designed a model that could explain how such materials could have been created. Ilan Blech was a professor at the Technion. Shortly after we published the paper, he left the Technion, went to California. But this paper was sent to a journal named Journal of Applied Physics. In those days, most scientists could not type. We had secretaries that would type from our handwriting. We wrote the papers by hand. We had the old guys, my generation, nod, they remember that. And so I had a secretary who typed it. Any mistake she made, she had to type the whole page again, or use the writing compound. Anyway, I put it in an envelope, put a stamp on it, and sent it to the Journal of Applied Physics. 2 weeks later, I received the paper back with a letter from the editor saying, "Dear Dr. Shechtman, thank you so much for your contribution to our journal. However, we have decided that your paper will not interest the community of physicists. Why don't you send it to a metallurgical journal?" Okay? So I sent it to a metallurgical journal named Metallurgical Transactions. It was accepted and published. But it was published 8 months later, deep into 1985. In the meantime, I spent the summer again at NBS, and I showed this paper to John Kahn, my host, and asked him, why do you think it was rejected? What's so wrong with this paper? So we had a debate and arguments, and I gave him a lot of information. And he said, "Oh, Danny, this is fantastic. Why don't we do something totally different? Publish only your findings from the first day, only the discovery, not the model, nothing else, and send it to a quick publication." Great. We did that. And that was the first paper that was published, but it was the second that was written, and a short version of the first one. And the names are my name, Ilan Blech, Denis Gratias, and John Kahn. Denis Gratias is an eminent scientist, mathematical crystallographer from France. At the time, he was in Vitry. Now he's another laboratory, and he's a great scientist and a great friend of mine. We sent this paper, and it was accepted and published in November 12, 1984. And when this was published, hell broke loose, because I started to get telephone calls and emails and you name it from all over the world. "Danny, we have it. Because in the paper, I explained exactly how I prepared my material. As I said before, a large community of young, eminent scientists around the world, mainly in France, because Denis Gratias brought it to France, but also in the United States, in Japan, in China, in many countries in the world, in the scientific world. People started to work on it, and it became a science very quickly. So this was the paper that made the difference. Now I have to explain to you what the icosahedral symmetry is. This is an icosahedron. It's a platonic body, and it has 6 5-fold axes, 10 3-fold, 15 2-fold. What does it mean? If you put your eye here and look to the center, you see that there is 5-fold rotation symmetry here. From here also 5-fold, from here also. 1, 2, 3, 4, 5, 6. These are the 6 axes. This is just the negative of that, so it doesn't count. And 10 3-fold. You look from here, 3-fold. You can turn it 120 degrees and it will look the same. And so on. This is an icosahedron. Some people prefer this explanation, which is even better. It's a football. You know, some of you know football. Messi, Maradona, yes? Okay. When I say that in South America, yeah! Anyway, this is the football. It's made of patches, pentagons and hexagons. And you clearly see that there is 5-fold rotation symmetry from this point of view, 2-fold rotation symmetry from this point of view, and 3-fold rotation symmetry from this point of view. Football, fullerenes, and icosahedron all have the same symmetry. Okay, now I have to explain to you what quasi-periodicity is. What is quasi-periodicity? And to know what quasi-periodicity is, I must take you back to the 13th century. And I want you to meet Mr. Fibonacci, Leonardo Fibonacci de Pisa, whose friends called him Blockhead But he was the greatest mathematician of his time, and 500 years later, he was still the greatest mathematician. What Fibonacci did was he wrote several books. One of them called Liber Abaci, book of mathematics. Okay? Liber Abaci. And in that book, he tried to convince the merchants in Italy to use the Indian numerals that the Muslims brought to Europe. And nobody wanted to use it. They used the old Roman numerals, which was very inconvenient. The Indian Muslim numerals were by far more convenient, and most of his book is dedicated to convincing the people, see how easy it is to work with a new system. But part of his book, a small part of his book, he described a very interesting experiment, and this is what leads us to quasi-periodicity. Leonardo, this is a drawing of him when he was young. Look at these wonderful eyes. And this is a picture, a real picture of a statue that stands on his grave, and he's buried just behind the inclined tower of Pisa. So if you go to see the inclined tower of Pisa, just behind it there is a graveyard under a roof, and this statue is there. It is higher, it's about 2 meters high. It's a big, big statue. Okay, enough of that. To know what quasi-periodicity is, we must start with Fibonacci rabbits. Fibonacci rabbits? Yes. So here are the Fibonacci rabbits. It's quasi-periodicity in one dimension, along a line. So here is the experiment that he designed. He said the following. Let's say that we have a female rabbit, and she has a husband or a boyfriend. He comes to visit her, goes back, now she's pregnant. And in the next month, she gives birth to a little one. In the third month, this mother gives birth to another little one. And this little one matures before it can reproduce. These are the rules. We can continue. In the fourth month, this mother gives birth to a little one. This little one matures, and this mother gives back to a little one. In the next month, this mother gives birth to a little one. This little one matures. This one gives birth to this little one. This one gives birth to this little one, and this one matures. These are the rules. So clearly there is order here. You understand the rules. You can continue this forever because you understand the order. And yet, if you look at any line, let's say at this line, you see that there is no periodicity here. I will show you. We have large, small, large, large, small, large, small, large, large, small, large, large, small, large, small, large, large, small, and so on and so forth. There is no motif of any size which repeats itself periodically. No periodicity. There is order, but no periodicity. This is quasi-periodicity in one dimension. Also, now that we are friends with Mr. Fibonacci di Pisa, let me just show you a few more things which are important to know. And this is very simple. These numbers are the number of rabbits in each month. So in this month, this is month 1, 2, 3, 4, 5. In the fifth month, we have 8 rabbits. In the sixth month, we have 13. Then 21. And so on. These are Fibonacci numbers. 1 plus 2 is 3. 2 plus 3 is 5. 5 plus 8 is 13. 13 plus 21 will have 34. 21 plus 34 will have 55. This is the Fibonacci series. And this is what this says. The number of rabbits in any given month equals the sum of the number of rabbits in the 2 previous months. Also, what is not obvious is the fact that if you go to the limit, when n goes to infinity, you go to infinity, then the number of rabbits in the last month divided by the number of rabbits in the previous month is this Fibonacci number, 1 plus 5 divided by 2. It's an irrational number, 1.68, and so on. So many, many digits behind it. And this is the number tau or phi, Fibonacci number, or it is called also tau. And it has many, many applications. A very, very interesting set of numbers. Okay, he published in the year 1202. That was quasi-periodicity in one dimension. What about 2 dimensions? Quasi-periodicity in 2 dimensions is Penrose tiles. Roger Penrose is an eminent scientist living in our time in England. mathematician, physicist, philosopher, amazing scientist. And he designed the Penrose tiles, which are two rhombi, one with 36 degrees here, one with 72 degrees. And if you join them together according to matching rules, certain matching rules, it means one arrow should touch one arrow in the same direction. Two arrows should touch two arrows in the same direction. If you do that, you can tile a two-dimensional space, and these are Penrose tiles. There are no spaces left, and this is quasi-periodicity in 2 dimensions. What about quasi-periodicity in 3 dimensions? These are called quasi-periodic crystals, and here is one of them. Quasi-periodic material is quasi-periodicity in 3 dimensions. Okay. Now you tell me, you want to think hard a little bit, or you don't want to think hard a little bit? Who wants to think hard a little bit? 2 people. 3, 4, maybe more? No. I will go over it in a jiffy, okay? Because it's really nice. The cut and project method, very quickly, for those who can think quickly. What you can do is listen quickly, listen carefully. You can take a high-dimensional space, make a cut in it and project, and produce, and the high-dimensional space is periodic, like this. This is a 2-dimensional space with periodicity, right? In every point you have a mathematical point, which is a point without dimension. You know what? Let's keep it. For the sake of time, anybody who wants private lesson can get it from me later on. Let's go to the story. When I started to talk about quasi-periodicity, actually I talk about 5-fold rotation symmetries and icosaedral symmetries and in crystals. And so people around me said, Danny, what do they teach you at the Technion? I mean, don't you know it's impossible? And the reactions were varied. John Kahn, my host, was very supportive. He was used to come to my office and say, Danny, this material is telling us something, and I challenge you to find out what it is. Positive. Negative. My group leader came to my office, and he had some comments, but in the finale, he came to my room, smiling sheepishly, putting a book of X-ray crystallography on my desk, and saying, Dr. Shechtman, please read this book, and you will know that what you are talking about cannot be. And I said to him, I know this book, I teach at the Technion, I don't need to read this book. I'm telling you, my material is not in the book. Took the book back, came back a couple of days later, and he said, Dr. Shechtman, you are a disgrace to my group. I cannot continue to, you have your name associated with mine. Please leave the group. So I left. And I moved to another group who was willing to adopt the scientific orphan. It sounds terrible now, but at the time, it was just an administrative step. He doesn't want me. Okay, another group wants me. Fine. Instead of reporting to this secretary, I report to that secretary. I don't even think I told my wife about it. But now it sounds traumatic. But this was the feeling, and the feeling was heavy because most people around me were talking bad things about me and about the Technion and about science in Israel in general. And if you want to know how I felt during this time, it was something like that. This was the feeling. I think it described better than words how I felt during that period of time. This was 1982 till 1984. In 1984, we published the first paper, and we had a growing community of scientists joining. They were the believers. This was the new brand of scientists, and they took the science to heights which I could not do myself. So you would think, okay, now it's a growing science, everybody agrees, not so fast. Because from 1984 to 1987, the International Union of Crystallography said, you bring us X-ray diffraction. You remember? X-ray diffraction. We don't believe in that electron microscopy stuff. I mean, that's not, it's not accurate, it's not precise, it's not, no. X-ray diffraction. To do X-ray diffraction from a single quasi-periodic crystal, you need a crystal of some size. A fraction of a millimeter will be good. We didn't have that. Our crystals were 1 micron in size. We needed to grow crystal. And in order to grow crystal, we needed to find stable quasi-periodic materials. In 1987, colleagues of mine in France and in Japan, jointly or separately, grew large enough crystal. They took beautiful picture of X-ray diffraction, and this is the picture. This one was taken by my colleague Anpeng Tsai in Japan, but the French people sent me a similar one. I showed this very picture in the meeting of the International Union of Crystallography in Perth, Australia, and then the community said, okay, Dr. Shechtman, now you're talking. They took these and formed a committee that redefined crystal. And you saw the redefinition of a crystal in the beginning of my talk. This was a paradigm shift in crystallography. This was it. Their acceptance of the International Union of Crystallography was the paradigm shift in crystallography. So you would think, okay, end of rejection, right? Not so fast. Because then there was Professor Linus Pauling and many other people. But he was the leader. And I'm glad that we have here the president of the American Chemical Society, because the American Chemical Society was behind Linus Pauling. And the American Chemical Society now counts something like 163,000 people. You can correct me if I am far off, but something like that, hundreds of thousands. I mean, this is a large community of eminent scientists. And Linus Pauling was the godfather of the American Chemical Society, and rightly so, because he was the greatest chemist of the United States during the 20th century. He was the greatest, no doubt about it. He wrote the books. He taught us so many things. He lacked one thing. He was not modest. He believed that he understood everything. He did not. He made mistakes. And some of his mistakes were huge mistakes, and he continued to fight. When they discovered the double helix of the DNA, he had a triple helix model, wrong stuff. And then, and I don't want to talk bad things about it, because I really think that he was one of the greatest scientists of the last century in general. So this is Professor Pauling. And Professor was standing on stages saying, there are no quasi-crystals, just quasi-scientists. Danny Shechtman is talking nonsense. What he thinks he sees is really twins in periodic lattice. And I knew from day one that there were no twins in my materials. And there are no twins in quasi-periodic materials. So this continued on and on and on and on. And the American Chemical Society was behind him. So, and I was in meetings of the American Chemical Society. This is a huge meeting. Thousands of people sit there. And Professor Pauling is the godfather. And he stands there on the stage and he said, Danny Shechtman is talking nonsense. He said, this is the model. A model of so many atoms. And you twin it here and here and here and here. This is what you get. A week later, somebody published a comment, no, Professor Pauling, it doesn't work. Your model is wrong. Oh, he said, okay, no problem. I have another model, which is larger and larger and larger. You can come closer and closer and closer to quasi-periodicity by having a larger and larger and larger model of periodic structure. And this is what he did. We had a lot of communications over the years. We met several times. I came to visit him in Palo Alto in his home. I gave him a lecture like this for one person. And at the end of this meeting, he said, Dr. Shechtman, I don't know how you do that. That means that he did not understand electron microscopy. He was an X-ray crystallographer. Now, if it were a student who tells me that he doesn't understand how I do that, I would say, why don't you go read a book? But Linus Pauling wrote the book, so I'm not going to tell him to read a book. But anyway, all I said was, in that particular meeting, Dr. Pauling, if you ever agree with me, don't keep it a secret. Make it public, please. Yeah. Professor Pauling died in 1994, and this was the end of resistance. I want, towards the end of my talk, I want to mention a few people who made seminal contribution. Roger Penrose, whom I mentioned. Ellen Mackay is also a British crystallographer. He took Penrose tiles and showed that they diffract sharp points in the reciprocal space. This was a major contribution, but he published his paper in Proceedings of a Russian Meeting in Russian. I didn't know about this paper. Most people didn't know about this paper. It became famous only after the discovery of quasi-periodic material. Ilan Blech, Denis Gratias, and John Kahn, these are the people that wrote the papers with me, so definitely seminal contribution. Last but not least, Dov Levin and Paul Steinhardt, who are two scientists who developed the tiling model, the mathematical model, as opposed to the Ilan Blech model, which is the physical model. Both are correct. This is a physical approach, mathematical approach. Very important contribution. Okay. Now I want to take you back to the days after the publication to show you the enthusiasm that you had. And this graph will explain that. I want to explain you what you see. This is, the year is 1986. Remember, it was the first paper was published at the end of 1984. So this is a year and a half after the publication. And this is the month, January, February, March, April. This is the month. Right? This is December. Here you have 1 over n. What is n? N is the pages in the bibliography. I have to explain. We hired, at NBS, we hired a secretary whose sole job was to collect all the papers on quasi-periodic materials from around the world and make a library. She was a librarian of quasi-periodicity. And every paper she received, she put it in her book, in the computer, page by page. So every page in the computer contains maybe 20 papers. Paper by this and this, where it was published, date, and so on. About 20 papers per page. So n is the number of pages in the bibliography. So when n equals 1, it means 20 papers. When n equals 10, it means 200 papers. My friend took, was drawn by hand on a piece of paper, and he said, okay, in February we had so many papers, 0.08, which means it's about 12 pages. 12 pages meaning 240 papers or something like that. And in March we had this, and so on and so on. In July, this is where we met for lunch, and he brought it to the lunch table, and I confiscated it from him. This is why you can see it. And as a good scientist, he connected all the x's with a straight line. And to our horror, we discovered that in December of 1986, the number of papers on quasi-periodic materials will reach infinity. It didn't happen. But this was the feeling that the world is really exploding around us. It was a fantastic feeling. To sum up, well, order was synonym to periodicity. Now we know that order can be periodic, it can be quasi-periodic, and this is open-ended. If somebody comes with something that says, I have discovered crystals which are not periodic, not quasi-periodic, but something else, we listen. And that's progress. Before I finish, I want to ask the first question, and I will also answer the first question. And then you can ask questions. And my question is, why is it that quasi-periodic materials were never discovered before 1982? 70 years of crystallography. Tens of thousands of eminent crystallographers and other scientists studied hundreds of thousands of crystals, and nobody saw quasi-periodic materials? Why? Why is it? Is it because they're very rare? Is it because they're not stable? You touch them, they disintegrate or transform? Is it because they're difficult to make, and I, with my magic hands, made one? Is it because they are made of rare elements? I don't know, praseodymium, gadolinium, and a touch of helmium in the corner? What is it? Why were they not seen before? Are they rare? Not at all. There are hundreds of them. There are hundreds of quasi-periodic material. In fact, they are very abundant. And there are several kinds of symmetries, icosahedral, decagonal. We don't have time to go, but there are groups of quasi-periodic material, different ones with different properties, with different crystallography. Here is a partial list of quasi-periodic composition based on aluminum alone. And none of it was seen and analyzed before. And there are many based on other elements. Maybe they are not stable. Well, many are not stable. What does it mean? It means that if you heat them up to a temperature of 350 degrees C or 400, they will transform into a stable periodic phase. But at room temperature, they're stable. And there are also many that are stable and they melt congruently. Somebody that melts congruently, meaning something that you heat it up, it will not transform into any other phase, and then it will melt. They melt congruently, some of them. All these melt congruently. So this is not it. It's not the instability. Maybe they're difficult to make. Well, not at all. You can make them by casting, you can make them by rapid solidification, by single crystal growth, by electrodeposition, by CVD, by PVD. Any method that you produce any material, you can make quasi-periodic material. It is easy to make them. Nothing to it. Very easy to make them. That's not the reason they were not seen before. Maybe they're made of rare elements. Not at all. They're made of iron, aluminum, chromium, copper, titanium, many other. Millions of tons of these elements are used every year in construction, in machine. I mean, these are abundant. We use these materials in large quantity. So why is it that quasi-periodic material were never discovered before 1982? Let me give you my answer. From now on, it's subjective. Up to now, it was objective. Now it's subjective. That's my point of view. Number one, quasi-periodic materials had to be discovered by TEM, transmission electron microscope, because the crystals were small. Too small to get a diffraction pattern by X-rays for one crystal. And if you have polycrystalline quasi-periodic material with many, many little crystals, and you take X-ray diffraction, you have rings in the diffraction. And you lose the rotational symmetry, and if you don't see the exceptional rotational symmetry, you cannot discover quasi-periodic material. TM, number one, transmission electron microscope. So you may say, okay, big deal. There are tens of thousands of people around the world using TEM. Why you? Well, using a TEM is not enough. Sorry. You have to be a professional. Let me tell you something which is really interesting and not good news. Of the tens of thousands of people that use electron microscopy around the world, very, very few become professional. Very few. I can testify that in my department, which are leaders in electron microscopy in Israel at the Technion, over the years in which thousands of people used our microscope, then we teach electron microscopy. Maybe we have produced 15 electron microscopists over a period of 50 years. 15 people. And they all have position in electron microscopy in Israel and around the world. Of 1,000, we produce a few. And those of you who know about electron microscopy can testify this is true. Very few become professionals. Even if you are not a professional, no chance that you can discover something really new and shocking. You have to be a professional. I was a professional. Tenacity. Tenacity means be like a Rottweiler dog. You bite, you don't let go. What does it mean? If you find something interesting, something unusual, don't say it's too complicated, I need to proceed on my way. Don't do that. Stick with it until you find out what it is. Now, in many cases, it will be an artifact, or it will be something that somebody discovered 35 years ago. In most cases. But sometimes, just sometimes, you made a wonderful discovery. Don't let go. Let me give an example. There is one professor in Europe who is a great electron microscopist, and he tells me the following story. He says, you know, one day, I sift through the plates, the electron microscope plates of my ex-students, and I pulled one and it's your picture of the diffraction pattern. I look at the date before you, taken by one of my students. So I call my student, by now a professor in another university. Hello, my ex-student, how are you doing? Thank you, professor, I'm fine, and how are you? He said, the professor, you know that you saw Danny Shechtman's diffraction pattern before Danny? He said, yes, professor, of course I know. He said, the professor, why didn't you tell me? Says the ex-student, you know, professor, if I told you, you would want me to stay for 2 more years on my PhD? I didn't want that. I wanted to finish my PhD. Okay? Tenacity. Don't let go. Just stick with it until you find out what it is. Believing in yourself. Now, this is part personality and part professionalism. If you are a professional and you repeated your experiments, or if you are a theoretician, you repeated your calculations. You repeated what you did before. And you prove to yourself as a professional that you are correct, then stand tall. You want to contradict me? This is fine. I'm listening. But you have to repeat my experiments. Show me what's wrong with my experiment. Don't tell me it's not in the book. That's not good enough. Books, we change every year. We change the books. Repeat my experiments. The people that objected me never repeated my experiments. The people that did made the community that created the community of quasi-periodic scientists. And last but not least, resilience. I can tell you that my promotion at the Technion were delayed a few years because somebody or some people that didn't like me very much. I can understand why. But there were people like that. One of them went to Linus Pauling and asked him, Professor Pauling, Danny Shechtman is going to be promoted at Technion. Is this a good idea? Pauling said, Danny Shechtman talks nonsense. He said, I don't know what the standards of the Technion are, but in my university, that doesn't go. So my promotion was delayed. And not once, several times. Resilience. Everything is fine at the end. So this is just a nice picture of quasi-periodic material taken by Ampeng Tsai, my colleague from Japan. This is scanning electron microscopy. And he painted them artificially to look like the cherry blossom that they like so much in Japan. And you can see here very nicely the 5-fold rotation symmetry, the 2-fold here, and the 3-fold here. Beautiful crystals. Thank you so much. Thank you.